So we continue with the chapter sound, and we are on the second part of the chapter, that is natural, damped and forced vibration along with resonance. So this is quite an important part of the chapter. So these are the different kinds of vibrations, that are the natural one, damped one and forced vibrations. These are the three kinds of vibrations, and a special kind of forced vibration is called as resonance. So let's see. Natural vibrations. The periodic vibrations of a body in absence of any external force on it are called the natural or free vibrations. We very well know that each and every object, each and every molecules are in a rhythmic kind of vibrations around their mean position. This vibration, what they are having, is called as the natural vibrations of it. So because basically these are the periodic vibrations of the body when they are not given, okay, they are in absence of any external force. If there is no external force given to the body and still the body is in a particular kind of a vibrational form, is called as the natural or free vibration. They are given an example. A body clamped at one point when disturbed slightly from its rest position starts vibrating. The vibrations so produced are called the natural or free vibration of the body. The period of vibration depends on the shape and size or structure of the body. The time period of the body is called as the natural period, and the frequency is called as the natural frequency. A body capable of vibrating has a constant natural frequency of its vibration, and its amplitude of vibration remains constant. The natural vibration of a body actually occurs only in vacuum because the presence of medium around the body offers some resistance, due to which the amplitude of vibration does not remain constant but is continuously decreasing. So as I said rightly, that suppose I take a string and suspend this particular pen, and if I just allow it to move, it will continuously move in a particular manner. So this movement of this particular pen, when suspended freely, can be said to be as its natural vibration or natural frequency of vibration. The time period is called as the natural period, and the frequency with which is traveling is called as the natural frequency. Normally it is seen that in our normal air, it is found that the body will not be vibrating properly in natural frequency because the air around us, or the air around this, will be acting as a dampening force or will be a resistive force, which will not allow this to move freely, and slowly and steadily it will come to rest. So that's the reason, if something like, for example, if you take even a swing is going to move till the time it is being pushed. The moment the pushing बंद कर दिया तो धीरे धीरे उसका amplitude कम होते जाएगा, and then finally it will stop. So the stopping of this thing is because of the resistive forces which are being given by the air around it. So that's why normally the natural frequency or the natural or free vibration is seen only in case of vacuum, where there is no resistive forces acting on the body. Okay. Otherwise, it will always be in a continuous decreasing order. So the examples of natural or free vibration: if a bob of simple pendulum is displaced slightly from its mean position, it starts vibrating with its natural frequency, which is determined by the length L of the pendulum and acceleration due to gravity G at the place. It is given by frequency is equal to 1 upon 2 pi root of L upon G upon L. Okay. So if I take a pendulum and if I just displace this slightly, I do not take it fully and distend it and go ahead, I just displace it slightly, then it is seen that the vibrations of the pendulum will be at its natural frequency, wherein the natural frequency could be found out by the formula F is equal to 1 upon 2 pi root of G upon L. Okay, this is the frequency. Why is this ulta? Because normally अपना क्या था, टाइम पीरियड t is equal to 2 pi root of L upon G, ये उल्टा है. क्यों है? because ये frequency है तो 1 upon t. So that's why frequency is given by this particular thing. It's a simple thing. So this is what you had studied in the 9th standard. This is the 10th standard. Reciprocal of that, that is frequency will be equal to 1 upon 2 pi root of g upon L. So that is how you are going to calculate the pendulum ka frequency. Different pendulum having different lengths will vibrate with different frequency. That is, they will have different natural frequency. A simple pendulum of length 1 meter on Earth's surface, where the acceleration due to gravity is 9.8 meter per second, has a natural frequency of 0.5 hertz. So we very well know it's called as a seconds pendulum, having the frequency 0.5 hertz. That is, 2 vibrations or 2 oscillations in 1 second is called as the seconds pendulum. So if that is when the pendulum is of a length of 1 meter and it is at a place where the gravitation force is 9.8 meter per second square. Secondly, a load suspended from a spring when stretched or compressed and then released starts vibrating with its natural frequency. Its frequency is determined by the hardness or constant force, constant K of the spring and the mass M of the load. F is equal to 1 upon 2 pi root of K upon M, which is not required. You don't require this formula. This was required because this is given to you much more easily because 9th SAM में इसको हम लोग ने पढ़ा है. So whereas this thing is not there. So it is just for your knowledge. Because we don't know anything about the constant of springs. The spring constant जो होता है, the free force constant K of the spring is not known to you. So let's not discuss that thing or confuse ourselves in that particular. The frequency will be different for the same load or different springs, and it with different loads of same spring. So yeah, so we can see that if I take a spring and I hold something and below it and then I release it, what will happen? It will just go like this. It will just go on going up and down like this. So that will be the way the spring is going to behave. The spring, there will be continuously up and down movement of so that up and down movement, the frequency of the up and down movement of that particular object by the spring is given by this particular formula that we don't worry about the formula, but it is given by a particular kind of a calculation, which also tells you that अगर मेरा लोड इंक्रीज हुआ तो भी फ्रीक्वेंसी चेंज होगा और अगर मेरा स्प्रिंग डिफरेंट हुआ तो भी मेरा फ्रीक्वेंसी चेंज होगा. सो द फ्रीक्वेंसी विल बी डिफरेंट फॉर डिफरेंट स्प्रिंग्स एंड फॉर डिफरेंट लोड्स. The third is when a tuning fork is struck against the hard rubber pad, it vibrates with its natural frequency. The vibration form longitudinal waves in air, which when reach our ears, sound is heard. This sound is of one single frequency. It is called as a pure note. Different tuning forks produce sound of different frequencies. So a tuning fork, we know the tuning fork, it's something like this. So this tuning fork will be like this, a thin steel tong, and that will be, इसको पकड़ के हम लोग इसको ऐसे मारेंगे तो ये V part इधर मारेंगे तो it will start vibrating and it is going to produce a particular kind of a sound. So that sound what will be there will be a single note or a true note or pure note, and it is that the tuning fork always produces a single note or a principal note and will always have of a particular frequency. So tuning fork is always having a particular frequency, and hence different frequencies there will be different kinds of tuning forks. So different tuning forks will be there for producing different frequencies. The fourth one, now this one is very important to understand, so just see to it. There will be certain questions which are normally asked based on this, so that's why it's important to understand this thing. When an air column in a flute on an organ pipe is made to vibrate, it vibrates with a natural frequency which is inversely proportional to the length of the air column. So first of all, what we have is when a particular flute or an organ pipe or something is being though उसके air column के हिसाब से the frequency will be there. The frequency is inversely proportional to the length of the air column. Okay, it is inversely proportional to the length of the air column. More the length of the air column, lesser the frequency, or lesser the air column, more the frequency. So in a flute, The note of different frequencies are produced by changing the effective length of the air column when different holes in it are closed. In an organ pipe of given length, open at both ends, different modes of vibrations are produced by blowing the air differently, and they are of frequencies in the ratio 1:2:3. While in an organ pipe with one end closed, the frequency of different modes are in the ratio 1:3:5. So there are two frequencies. Frequency will be in the range of 1:2:3 for both end open, and frequency will be in the ratio 1:3:5 with one end open. Okay, let's understand what exactly we do mean about this thing. So you must have seen flutes. तो फ्लूट कैसा रहता है? एक फ्लूट ऐसा है जो पूरा का पूरा ऐसा open है, and you are blowing it like this. Okay, you are playing it like this. When you are playing it like this, so this is open on both ends. That is a mouth, that is particular kind of a flute or any kind of a organ pipe which is open on both ends. The other one is the one which is open on one end. तो जो ऐसा है तो क्या है? Open on only one end. दूसरा end तो हमारे mouth में तो only one end है. So in this case, if the range, if the holes are there 1, 2, 3, 4, तो जैसे जैसे मेरा length का जो ratio है, तो the ratio of the frequency will be directly with the 1:2:3. So they are given over here in an organ pipe of given length, open at both ends. Different modes of vibration are produced by blowing the air differently, and they are of the frequencies in the ratio 1:2:3. So the ratio of the frequency will be in the 1:2:3 with the length of that air column. So air column के हिसाब से 1:1, 1:2:3 के ratio में the frequency of the sound produced is going to be dependent on. Whereas in case of one end closed and other end open, उसके अंदर the frequency of the generation of sound will be the ratio of 1:3:5. So it will be 1:3:5 in case of one end closed, and both end open will be 1:2:3. The fifth one is when the string of the instrument like sitar, sonometer, violin, etc. is once plugged, the transverse vibration of the definite natural frequency are produced in the string. The frequency f of the vibration in a stretched string depends on first the length. So in case of string instruments, so this was in case of wind instruments. Now in case of string instruments, the first one, so in string, frequency is proportional to 1/L. Yeah, definitely dependent on the length of the wire. जितना बड़ा string उतना ज़्यादा जितना लंबा string उतना कम frequency, जितना छोटा string उतना ज़्यादा frequency. So the length L is the spring, the vibration, the frequency of vibration will depend on the length, that is F is proportional to 1/L. Second, the radius of the string, that is the thickness of the string. So accordingly it will be, again second will be F is inversely proportional to the radius. So again it will be, if the radius is more, the frequency is less. If the radius is less, the frequency will be more. So for thinner wires, the frequency will be higher. For thicker wires, the frequency will be lower. Okay, low frequency, thick wire; high frequency, thin wire. The third is tension of the string. The third one is the tension. So F is proportional to the tension of the string. Tension यानी वो string कितना tight है, and that is directly. अगर जितना ज़्यादा tight उतना ज़्यादा frequency, जितना कम tight उतना कम frequency. So the tension of the string T is proportional to the square root of this. The only thing is that it is not the directly related, it is the square root of this. So if the tightness is doubled, or in fact if the tightness is 4 times, the frequency will be doubled. Thus the frequency of the note produced by the string stretched between the ends is given by f is equals to 1 upon 2l upon into root of t upon pi r squared. Now this is not required, so I will not write it because it's not required. You just need to know that what is the relationship between the frequency and the length, frequency and the thickness and the radius, and frequency about the frequency and the tension. You don't have the part of the equation which is given here, where d is the density of the material and of the string, and pi r square d is equals to m is the mass of the unit length of the string. Thus the frequency f of the note can be increased. So this is the important part. The important part is, how do we increase the frequency of the note of vibration of in a string instrument? Is first is decrease the length of the string. Of course, frequency increase करने के क्या करो? Length को decrease करो. Decrease the length, frequency will increase. Secondly, decrease the radius. If you decrease the radius, the frequency will increase. So decrease the radius or thickness. So if you decrease the radius means decrease the thickness and the frequency will increase. And third is increasing the tension. If you increase the tension, the frequency will also increase. So accordingly, we see that to increase the frequency of vibration of increase the frequency of the sound produced by a string instrument, you can either, first thing is decrease the length of the string, or decrease the thickness of the string, or you increase the tension of the string. Sixth one, when we strike the keys of a piano, various strings are set in vibration, each at its own natural frequency, because they are of different thickness and under different tension. So yeah, in key piano also there are too many different strings going inside the piano, which will be set into vibrations at the time, and because of the different strings with the different thickness and the different lengths, there will be different frequency which will be generated in the piano. Seventh one, again an important point. A string of a given length stretched between its ends under a given tension can be made to vibrate in different modes by plugging the string at different points. If the string is plugged in the middle, the string vibrates in one loop as shown in figure 7.5a. This vibration is called as the principal note or frequency F. So let's see this. I got three strings over here. One string, second string, third string. This is tightly sealed over here, and then I take my finger and I just plug this string at the center. If I plug the string at the center, the string is going to vibrate forming just one loop. Okay, वो सिर्फ ऐसा बीच में से एक लूप आएगा, just one loop. Okay, they will be just ये बीच में से एक plug किया तो सिर्फ ऐसे एक लूप आएगा, सिर्फ ऐसा लूप आएगा. Okay, so this will be just one loop, and this particular loop what we are having is of frequency is equals to F, and this is called as the principal note. Okay, this is the principal note. Okay, if I plug it at the center. So if the string is plugged in the middle, the string vibrates in one loop as shown in the figure. This vibration is called as the principal note of frequency F. If the string is plugged at 1/4 length of string from one end, it vibrates in two loops. So if I plug it 1/4, यानी ये middle था इसके बीच में यहाँ पे, if I plug it over here, then it is going to be moving in this way, that it goes here, comes here, 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 and here. So you can see over here, this one frequency will be equal to 2f. Okay, the frequency over here will be 2f because there are two waves in this particular part, so 2f, and this is called as first subsidiary note. That's called as the first subsidiary note. So this vibration is called as the first subsidiary note. So if the string is plugged at 1/4 length of the string from one end, it vibrates in two loops. This vibration is called as first subsidiary note. Oh, made a mistake. I was making loop, I made a wave, so that's a problem. ये सेंटर है, यानी एक लूप यहाँ से ऐसे जाएगा, जो ऐसे करके ऐसे जाएगा, और वही चीज जब भी वाइब्रेट नीचे होगा तो इट विल बी लाइक दिस एंड लाइक दिस. सो दिस इज फ्रीक्वेंसी 2f and for subsidiary node. Now, similarly, if the string is plugged at 1/6 length of the string from one end, it vibrates in 3 loops as shown in the figure. So then it will be in 3 loops. So that will be in 3 loops. So this is frequency is equal to 3f, and this second subsidiary node. Okay, so vibrates in 3 loops as shown in the figure. This vibration is called as second subsidiary of the frequency 3f. Thus, the different modes of vibration in the stretched string are in the frequency of the ratio 1f, 2f, and 3f. If L is the length of the string stretched between its ends, the wavelength of the different modes in A, B, and C will be 2L, 2L upon 2, and 2L upon 3. This will be one length, so it will be 2L will be the total wavelength. One wavelength will be 2L. यहाँ पे कितना wavelength आएगा? So 2L upon 2, so 2L upon 2, and here will be 2L upon 3. That will be the ratio. That's why they will be in the ratio 3:2:1. So the wavelength ratio of the frequency का wave ratio is 1:2:3, and the wavelength का ratio is 3:2:1. Okay, that is the ratio of the frequency and the wavelength. Okay, so these were the 7 points of the different examples of the natural frequency. So now, nature of natural vibrations. So natural vibrations, of course, it is natural only, as I told you, in the vacuum. So when in the vacuum, yeah, natural vibration is possible, but if the vacuum is not available, then the vibration is going to be of different types. So that is what we are going to study now. Now, the natural vibration are simple harmonic vibrations under the restoring force, the amplitude and vibration of which remains constant. So we very well know that what is in the natural vibration, the amplitude, the frequency, everything going to remain constant because there is no external force acting on it. So whatever is there is a natural frequency which is going to be the simple harmonic motion. It is called as simple harmonic motion or simple harmonic vibrations under the restoring force. That is the continuous kind of a restoring force of the body itself, which is not connected to any external force. Once body starts vibrating, it continues its vibration with the small amplitude and same frequency forever. So when it is in natural frequency, if there is no external force acting on the body, then the vibration is going to be as it is. It is going to vibrate with the same frequency, same amplitude for on and on and on forever. Okay. The figure 7.6 shows the displacement time graph of a natural free vibration of an ideal condition. So in ideal condition, the vibration is such that the amplitude, the wavelength, everything will be perfect. They will be just going in the same manner continuously throughout the life cycle. So that will be, in that particular point, is an ideal kind of a simple harmonic vibration. The vibration of a constant amplitude can only occur only in vacuum. Since in practice it is impossible to have vacuum, it is very difficult to realize such vibrations in practice. In practice, the surrounding medium offers the resistance of friction to the motion, so the energy of vibrating body continuously decreases, due to which the amplitude of motion gradually decreases. So isn't that the vibration is going to remain constant only if it is in vacuum, but normally it is not possible to have vacuum around any particular moving body. That's the reason we cannot exactly experience the natural frequency. But So what happens in normal condition would be there will be the air or the resistive forces around which this resistive forces will act on the uh, waveform, and accordingly the wave will have a decrease in its amplitude. A gradual decrease in the amplitude will take place, and which will be called as damped vibration. So that is what we study next, is the damped vibration. In a common experience, that when a body is made to vibrate in a medium, the amplitude of vibrating body continuously decreases with time, and ultimately the body stops vibrating. Such vibrations are called as damped vibrations. Thus, a periodic vibration of the body of decreasing amplitude in presence of resistive forces are called as damped vibrations. So yes, a periodic vibrations or a natural vibrations which are going to keep on deteriorating or decrease in its amplitude due to the resistive forces around it is called as a damped vibration. So if we see a damped vibration, the damped vibration will be such that अगर ये एक natural frequency अगर इस तरह से है that it is continuously going to be of the same amplitude and this one, the damped vibration of the same thing will be such that it is going to start with this way, but it is going to keep on decreasing in the size and go on becoming almost stops at a particular point. So that's why in damped vibration two forces act on the body: the restoring force and the frictional or resistive force due to the surrounding medium. The amplitude of motion decreases due to the friction force. Say restoring force will allow it to go on in this manner. Okay, it is because of the restoring force the natural frequency is going to take place. But the restoring force के against अगर vibration है, friction है, तो friction क्या करेगा? Restoring force को धीरे धीरे कम करते जाएगा. And because of the decrease in the restoring force, that's why it is going to become damped like this. Okay. In a damped vibration, two forces acting on the body, that is restoring force and the frictional force due to the surrounding medium. The amplitude of motion decreases due to the friction force. The friction force at any instant is proportional to the velocity of the body, and it has a tendency to resist the motion. As a result, the energy of the vibrating body continuously dissipates in doing work against the force of friction, and so its amplitude gradually decreases. After some time, when it has lost all its energy, it stops vibrating. The energy lost by vibrating body changes continuously into heat energy and gets dissipated in the surrounding medium. The rate at which the energy is lost to the surrounding or the rate of decrease in amplitude depends on the nature, that is viscosity, density, etc. of the surrounding medium, and also on the shape and size of the vibrating body. For example, figure 7.1 shows the displacement time graph of a body executing the damped vibration. So you can see that the dampening of the vibrations is going to depend upon the factors that what is the density of the material medium through which this particular vibration is taking place. If it is air, it also depends upon the shape and the size of the material. Like for example, if we are talking about a particular, let's say a swing. So in a swing, when somebody is not sitting on the swing and is just moving, that means the swing is going to cut the air properly, so the friction will be slightly less, so it is going to remain oscillating for a longer period of time, okay, if nobody is sitting on it. But if there is somebody sitting on it, then definitely what happens, the body itself is also going to be a part and parcel of the friction being caused between the air and the body, and hence it is going to come to rest much quickly as compared to what the swing would have come to rest when it was completely empty. So that's why it is going to so mainly what happens is the energy which is going to the restoring force, the energy which with it is moving, then energy is slowly getting dissipated as heat energy in the surrounding, and as the heat energy it is getting dissipated, there is a reduction in the energy which is the reduction in the dampening force, and hence the a reduction in the restoring force, and hence the dampening of the wave takes place. So that's why the rate at which the energy is lost is dependent on the nature, that is the viscosity and density, and also the shape and size of the medium. Examples of damped vibration: when a slim branch of tree is pulled and then released, it makes the damp vibration. So you can see, you can take a branch, you hung it over here and then you release it. What happens to the branch? It's just going to go like this, like this, like this, like this, and then slowly करके वो ऐसा रुक जाएगा. तो ये जो movement है, ऐसे करते 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 slow होके, that is nothing but damped vibration. A tuning fork when stroked on a rubber pad executes the damped vibration, and of course if you take a tuning fork, it is just when vibrating and then slowly it deteriorates and it becomes steady. So that is a damped vibration. A simple pendulum oscillating in air or any other medium executes the damped vibration. So pendulum also stops after some time, it's also damped vibration. The vibration of a spring having a mass at its end is in air, also damped vibration. So spring लिया और उसको hang कर देगा तो धीरे धीरे rest पे आता है. That is also damped vibration. So all these are examples of damped vibration. So we see the differentiation between natural frequency and vibration and damped vibration. The amplitude of the natural vibration remains constant and the vibration continues forever, whereas damped vibration, the amplitude of the damped vibration gradually decreases with time and ultimately the vibration ceases. Natural vibration, there is no loss of energy in the natural vibration. In damped vibration, each vibration, there is some loss of energy in the form of heat. Natural vibration, no external force acts on the vibrating body. The vibration are only under the restoring force. So there is no external force given to the body. So it is just the restoring force which is making it to move. Whereas in case of damped vibration, in addition to the restoring force, a frictional or dampening force acts on the body to oppose its motion. So there is a opposite thing. It is not allowing to move. It is stopping that thing, and that is the option. That is the frictional force which is dampening it. Of course, there is a restoring force which is making it move, but there is a dampening force which is, or the frictional force which is stopping it to move. Natural vibration, the frequency of vibration depends on the size and shape of the body and remains constant, whereas the frequency of the vibration is less than the natural frequency and that decreases. The decrease in the frequency depends on the dampening force. So this is about the damped vibration and the distinction between natural vibration and damped vibration. We now move on to the force vibration, but in the next video.